Okay, hi everyone. I'm helping the authors to present this paper because they cannot get here. The title of this paper is UniMem, Redesigning Disaggregated Memory with a Unified Local Remote Memory Hierarchy. I will introduce the work from these 4 parts. Disaggregated memory has attracted great attention recently because it has high memory capacity, elastic resource scaling, and high resource efficiency. It separates computing and memory resources into compute nodes and memory nodes. The compute nodes have powerful computing resources, but only have a small piece of local memory, while the memory nodes have massive memory, but only with very little compute cores. And there is a high-speed network between the compute nodes and memory nodes. The network has both high bandwidth and low latency. Disaggregated memory system is responsible for exposing the remote memory resources to the workloads run on the compute node. There are 3 types of designs. Object-based disaggregation memory system expose a key value or data structure-based interface for these workloads, so that it can facilitate the fine-grained control of the remote data. But they need a large number of code changes to transform the original workload to new interfaces. To improve the capability, page-based systems rely on the traditional OS mechanisms like the virtual memory subsystem or virtual file system, so that this workload can leverage remote memory without modifying the user code. But they suffer from the performance degradation because of the expensive kernel and data amplification. To ensure both transparency and good performance, cache-coherent-based systems are proposed. This approach leverages the cache-coherent accelerator to provide remote memory as local physical memory. The emerging interconnects, such as the CXL and the CCIX, realize the cache coherent between the CPU and the accelerator. Thus, they can provide remote memory in fine granularity and application transparent manner. However, there are 2 fundamental limitations of the existing cache-coherent-based systems. The first one is the overhead from the indirection layer. The cache-coherent-based systems. In the cache-coherent-based systems, the accelerator exposes a fake physical address space that maps in the host physical memory space. The pages of this fake physical memory can be allocated to workload as the host local memory and are always marked as present in the workload's page table. When the CPU cache miss on the fake physical memory, the CPU cache miss event is forwarded to the cache-coherent accelerator. The accelerator will first translate the fake physical memory address to remote memory address through a hash table lookup or remote memory management unit, and then fetch the specific cache line from either the local cache and the remote memory. And this fake physical memory scheme and address translation will form an indirection layer. It introduces extra latency for every CPU cache miss event on the remote memory. We now analyze the extra latency introduced by this indirection layer. We assume using CXL as the cache-coherent protocol that connects CPU and the accelerator. The round-trip latency of a CPU cache miss event across the CXL link is 50 nanoseconds, according to some related works. We assume the address translation for the cache-coherent-based system is implemented by the hash table lookup. Previous work have implemented high-performance hash tables on FPGA, showing that the search latency over the hash table ranges from 14 nanoseconds to 243 nanoseconds. This time are measured on the state-of-the-art devices like Intel Stratex FPGA and Xilinx Alivio FPGA. The indirection layer introduces non-negligible latency to remote memory access. We further conduct a simulated experiment to investigate the impact of the indirection layer. We use UNIX perf to record the number of cache miss events of the CPU gas level cache and the time of running the workload on the host memory. Since each CPU cache miss event will undergo a round trip on CXL interconnect and introduce an additional address translation in the accelerator, we use the number of cache miss events to calculate the total runtime overhead of the interconnect round trip and the address translation. We set the latency of the address translation in the accelerator to 128 nanoseconds. This result shows that the address translation can occupy the total runtime from 18% to 58%, and it is non-negligible. The second limitation of existing system is the cache pollution and thrashing in local cache. Disaggregated memory system use local memory as data cache for remote memory. This makes the local cache a crucial component for system performance. However, they overlook the harm of cache pollution that comes from the limited local cache capacity. Compute nodes are typically equipped with a small piece of memory, for example, around 10 gigabytes. The cache size is much smaller than the workload footprint. Memory-intensive workloads with a large working size will compete for the limited local memory resources if these workloads are running on the same compute nodes. A smaller cache means a shorter observation window for the access pattern of the workloads, which lowers the likelihood of identifying the frequently used data in the cache. Furthermore, the frequently used data might devolve into one-hit wonder, which is not requested after insertion. This will pollute the cache and lead to inferior local cache efficiency. The third limitation of existing system is the neglect of local memory resources. There are two kinds of local memory resources in compute node: the host memory and the device attached memory. The host memory can provide lower access latency than the device attached memory. Existing systems only utilize the device attached memory as local cache, which neglects the fast host memory. Motivated by these examples, we present UniMem. It is a cache-coherent-based disaggregated memory system within a unified local remote memory hierarchy. To eliminate the indirection layer overhead on the remote memory accessing path, UniMem proposes a unified local remote memory hierarchy with shadow region and remote balloon. To satisfy the CPU cache miss event from the host on compute node, UniMem constructs the filter cache on the device attached memory of cache-coherent accelerator. And to thoroughly explore the limited fast host memory for the optimal system efficiency, UniMem proposes fully use the page table promotion scheme to mitigate data between host memory and device attached memory. To eliminate the extra address translation, UniMem introduced shadow region. Shadow region is a range of physical memory space in the compute node. It leverages PCIe-based address registers of the accelerators to assign a physical memory space region to each compute node. Thus, the memory request is redirected to the accelerator when it misses the CPU cache. The physical memory address come along with CPU cache miss event can be used to look up corresponding data in the local cache or the remote memory pool directly. The indirection layer not only exposes the remote memory to the compute node, but also isolates them from each other. Remote balloon implements compute node isolation by the help of memory hotplug feature. The memory hotplug feature supports physical memory onlining and offlining at runtime. During the power-up process of compute nodes, the specific physical space of shadow region is initialized to be offline. At this time, remote memory is unavailable to compute nodes. When a compute node allocates remote memory from the remote one, it aligns the corresponding remote memory range within the shadow range of the specific compute node. This allocated range keeps offlines in other compute nodes for isolation. The unified local remote memory hierarchy eliminates actual address translation and implements lightweight isolation. The limited local memory capacity poses a challenge in designing an efficient local cache for memory-intensive workloads. Filter cache partitions cache space into active list and inactive list. The active list can take up most of the cache space to reserve the reused data to absorb as much remote access as possible. It can grow up to 90% of the cache space. The inactive list and default queue acts as a guard to prevent active list from pollution. Filter cache regulates the inactive list as this takes up to 10% of the cache space for observing the reused data. The default queue is used to extend the inactive list logically for longer observation window. When the block is fetched from remote memory, filter cache first searches the default queue to verify whether the block is previously evicted from the active or inactive list. The block is then inserted at the head of the active list or inactive list, according to if it is recorded to the default queue. When the block is in the inactive list, it is promoted to the head of the active list as reused data. And when the block is evicted from the inactive or active list, the block is written back to the remote memory if it is modified, and the evict block is recorded in the default queue. This filter cache can identify reused data and prevent local cache from polluting and thrashing. The third problem is existing work do not explore the fast host memory. The compute nodes include two types of local memory resources, the device-attached memory and host memory. Because of the interconnect overhead, it shows high latency to access the device-attached memory compared to the host memory. It is essential to explore the fast host memory and harmonize it with the device-attached memory. There are two problems that we need to solve. First is a mismatch of cache block size between the device-attached memory and host memory. The cache block size in the device-attached memory can be set up to any size. In filter cache, we set the cache block size to 512 bytes. The host memory is constrained to buffer data in the page. The host memory is constrained to the buffered data in the page due to the hardware restrictions such as MMU and the TLB. Second is the data amplification in page granularity could consume a significant amount of cache space for unnecessary data. This phenomenon is known as hotness fragment caused by different access frequency of the subpage within a page. Simply promoting data in page granularity from the device-attached memory to host memory in terms of page hotness might be suboptimal. We assign a hotness score to each subpage based on the list they reside in. The subpage in active list is given the highest score, while the subpage in the default queue receives the lowest score. A frequently used page with high hotness score and low variance is considered more appropriate to be promoted to the host memory. Fully used page promotion scheme explores the two kinds of local memory resources thoroughly. Next is the evaluation of UniMem. We conduct comprehensive experiments to evaluate the performance of UniMem through simulation. For comparison systems, we choose the state-of-the-art cache-coherent-based disaggregated memory system, CONA and its variants. We evaluate them use memory-intensive workloads. We also break down UniMem to demonstrate the efficiency gained by each design technique. We first evaluate the average memory access time of different workloads on the disaggregated memory system. The average memory access time is short for AMAT. We find that UniMem outperforms other systems in all time. As the local cache capacity decreases, UniMem's speed up will be larger. Short region and remote balloon contribute to an average improvement of 7% compared to CONA and its variants. This is credited to the remote memory mechanism of UniMem, which eliminates the extra address translation overhead. Filter cache and fully used page promotion specifically enhance the system performance in low cache capacity scenarios. The reason is that the final cache block size used in filter cache can lead to more local cache miss events in the abundant capacity scenario, but will be more efficient with the limited cache capacity. To get further on local cache efficiency, we evaluate UniMem against other systems based on the data amplification. The goal of data amplification means a more efficient local cache mechanism. It shows that a reduction in the local cache size leads to an increase in data amplification for all systems. The data amplification of UniMem maintains an average of 2.6 times the working set size, and the data amplification of UniMem is minimally affected by the reduction in the local cache capacity. The underlying reasons are twofold. On the one hand, the local cache mechanism of UniMem presents high cache efficiency than other systems, particularly in the scenarios with limited cache space. On the other hand, UniMem adopts a finer cache granularity than other systems. It means that each time a local cache miss occurs, UniMem can fetch less data from the remote memory pool. We further evaluate the performance benefit of UniMem under several memory-intensive workloads, which simulates the concurrent execution of multiple workloads. The memory access operations from different workloads will compete for the local cache. It aims to demonstrate the system performance of disaggregated memory systems in a more realistic scenario. UniMem presents the lowest AMAT compared to CONA and CONA PC. For the data amplification, UniMem achieves the lowest data amplification in the scenario with limited local cache capacity. On both metrics, UniMem presents the least impact for reduction of local cache capacity in the mixed workload scenario. Finally is our conclusion. Our observation indicates that extra indirection layer overhead and the inefficiency of local cache mechanism can have a large impact on the performance of remote data. To address these limitations, we propose UniMem. It is a cache-coherent-based disaggregated memory system within a unified local remote memory hierarchy. UniMem replaces indirection layer with shadow region and remote balloon. UniMem carefully reorganizes the host memory and device-attached memory to construct a tiered local cache for remote memory. Evaluation results demonstrate that UniMem is an efficient solution that can bring significant performance improvement across a variety of memory-intensive workloads. And thanks for listening. If you have questions, you can just email Yijie with this email address. Thank you very much.